All right, so when we were looking at kinematics, we said we can talk about how to deal with kinematics graphically. There are two equations, one that's a derivative version that's going to tell us about the slope on an x versus t plot. That's going to be the x component of the velocity. But we said we can rewrite this, right, multiply the dt over, integrate both sides, and we end up with an integral version of the same equation. And graphically dealing with this integral version, so any equation of this form basically says this quantity over here on the left is going to be given by the area under the curve, that's what the integral sign is telling us, on a velocity versus time plot. And so this is a velocity, x component of the velocity versus time. We take the area under the curve. Again, we're going to have a negative piece of area here, a positive piece of area here. So we've already talked about graphically how we deal with equations that have this form. And of course, our work equation has this form. So we've got that the work is equal to the integral from some initial position and some final position of f dx. So we want the x component of the force times a little displacement in the x direction. So this says we need to go look at a force versus position plot. So here's a force versus position plot. And again, the area under the curve here then will be the work. So we've got a force that's doing negative work over this little section as it moves from this position 1 to some whatever this position is here. And then we've got positive work being done by the force in this case. So notice it's doing negative work when the force is negative but the displacement is positive, right? We're moving this way to the right means moving with a positive displacement. So this says negative force, positive displacement. That means force and displacement point in opposite directions. Sure enough, we get negative work. Here, all the force values are positive, the displacement's positive, so force and displacement point in the same direction, we get positive work. So we know how graphically to deal with things that have this form, and our equation for work, our definition for work, has this same form. So again, we know graphically how to deal with it. The work's just going to be the area under the curve of a force versus position plot. Now, we did talk about the work done by a particular kind of force. So we talked about the work done by a conservative force and said, okay, well, that's just going to be the integral of the conservative force times dx as you go from some initial position to some final position. And we said this is equal to the negative change in potential energy. So basically we can take this equation and notice that it has effectively the same form that we've been talking about. The only difference is that there's this minus sign. Well, we know that we can take this equation and sort of undo it. So instead of being in its integral form, we take it back to its derivative form. So let's do the same thing with our equation for the change in potential. So the derivative version of this equation, when we undo the integral and rearrange our terms, says that the conservative force is going to be equal to negative the derivative of the potential energy with respect to position. And again, we know how to deal with this. This is, graphically, this says that the conservative force is going to be equal to negative the slope of the tangent line on a potential energy versus position plot. So here, if I've got a potential energy versus position plot, so potential energy is on my vertical axis, positions on my horizontal axis, then looking at the slope at any point, again, well here, what we're missing is the slope itself isn't the force. The slope itself actually happens to be negative the force. So there's a minus sign that should be in here. So this is a positive slope, but that positive slope would actually correspond to a negative force at this position. Here, at this particular position, at x2, we notice that the slope basically is 0, which is telling us that the force is 0. So for starters, one of the things that we recognize is that What does it mean for the force to be zero? Well, that's what we call an equilibrium point. That says that we're in equilibrium because the force is zero, and that the maxima and minima of our curve are going to of the potential energy curve are going to correspond to these equilibrium points. And there are two types of equilibrium points that we can have. So notice the question here: how many equilibrium points are there in the plot below? Well, we've got a minima, we've got a maxima, we've got a minima, so we've got 3 points, and 2 of them are known as stable points. One of them is known as an unstable equilibrium. So we've got 3 equilibrium points, 2 stable equilibrium, 1 unstable equilibrium. So the difference between a stable and an unstable equilibrium is basically here. Notice if I move in the positive direction, well, I've got a positive slope. Positive slope with the minus sign tells me I've got a negative force. So when I move in the positive direction, I've got a force that points back in the negative, which means basically it's going to try and take me back towards this particular point here. So our stable equilibria are places where we're sitting at the bottom, right? There are minima, because when we move away from that equilibrium point, we actually have a force that tries to get us back towards equilibrium. Our unstable equilibrium, well, if you try and move this away, so move it in the positive direction, we've got a negative slope here, which means we've got a positive force. So negative slope, positive force, so you've moved in the positive direction, but you have a positive force, that's just going to keep going. So our unstable equilibrium, the force is once you nudge it away from that equilibrium point, it's actually going to continue to go. Our stable equilibrium, you've got a force that's going to try and get it back towards the equilibrium point. So what can a potential energy plot tell us about the kinetic energy? And there are a couple important things that it can, but the first thing that we want to recognize is that basically what we'll do is we'll say, well, let's assume that the energy is constant, and so we don't have any work being done by non-conservative forces. Then our energy line is basically just going to be a flat line across this plot. So here's a particular situation where we're saying that our particle has an energy of 3 joules, and we know that the total mechanical energy is equal to kinetic plus potential. So I can take any point along this plot and say, well, if I know what the potential energy is, say here the potential energy happens to be 0, so at 2 meters the potential energy is 0. If the total energy is 3 joules and the potential energy is 0 joules, then this tells me that at 2 meters the kinetic energy is just 3 joules, right? It's 3 joules worth of kinetic energy plus 0 joules worth of potential energy is going to give me my total energy of 3 joules. Okay? Now, what this means is I'm now bounded, my particle is bounded by these 2 points, because to get to places over here would actually require negative potential energies. So again, if I'm, say, sitting at this point where the potential energy is 4 joules, well, the potential energy being 4 joules means to get a total energy of 3 joules means I've got to have a kinetic energy of -1. And kinetic energy can't ever be negative. Right? We're taking a positive number 1/2 times a positive number mass times a speed squared. It's always got to be positive. So basically to get into this region over here or this region over here would require a negative kinetic energy. That can't happen. You notice at the turning points, my total energy is equal to the potential energy. So the turning points basically are the places where the kinetic energy is 0. If the kinetic energy is 0, that means the speed is 0. And the speed is 0 because our object is coming to a stop at these points because all it can do is turn around and go back in the other direction. So if I release a point here, it'll speed up, move all the way over to here, slow down, stop right when it gets to this point, and then the only thing it can do is turn around and come back the other way. And so my particle can move back and forth between these 2 turning points, but it can't ever get outside them. It's part of what's dictated by what's going on with the energy. So notice that part of what happens here is as I come lower and lower in the curve, that means that the potential energy becomes less and less, which means the kinetic energy becomes more and more. So the larger the kinetic energy is, the faster my particle has to move. So at these particular minima here, my particle is moving as fast as it ever will, because that's the point where the potential energy is lowest. So here, the potential energy is -1. Right? At these 2 points, the minima on my curve, the potential energy value is -1, which means my kinetic energy value, if the total energy is 3, my kinetic energy has got to be 4 joules, so that my 4 joules plus -1 joules still adds up to give me my total mechanical energy of 3 joules. So 4 joules of kinetic energy here means that my particle has as much kinetic energy as it ever will. Right? It had 3 joules here, down to 4 joules, back up to 3 joules, something less than 3 joules. So it just has the most kinetic energy at these particular points at the bottom. So the object moves fastest as it goes through the minima of my potential energy curve. And then you'll notice that it's sort of only labeled for these 2 points in here, but certainly for any of these points on this region, we said, well, where we've got positive slopes, that means we've got negative forces. And where we've got negative slopes, that means we've got positive forces. So one way to think about this is, so as our particle starts here and moves in this direction, well, it's got a negative slope, which means it's got a positive force. Positive force moving in the positive direction means that it will be speeding up, and it's going to speed up all the way until it gets to this minima point. And then notice that minima point, that is the equilibrium, that's where the force equals 0, so the force is changing and going from being a positive force to a negative force. And so now as my object continues to move in the positive direction, but now a negative force, a force that's pointing back in the negative direction, is acting on it, it's going to slow down. It's going to keep slowing down until it gets to this equilibrium point. And now the force will change directions again, and it'll speed back up because it's moving in the positive direction now with a positive force. And it'll keep speeding up until it gets to this equilibrium point. The force will change directions again. So here we've got a positive slope, which means a negative force. And so my negative force will act on my particle as it moves in the positive direction to slow it down up until it gets to the turning point, and that's where it will stop. So the sort of our understanding of how to read what's going on with the force in terms of the slope actually folds in quite nicely into thinking about what's going on with the kinetic energy. And so this is one of the things that we'll work on in class today, about making sure we're understanding how to read potential energy versus position plots.